Okay, let's resume. So the next chapter, we're almost done with all the chapters in the textbook, so which is a good run. The next chapter is going to take hypothesis testing one more step, and we're going to compare two populations. Now, obviously, you can compare 3, 4, 5, 10 populations, right? That's kind of the lingering question. We will address that with ANOVA, okay, once we want to do more populations. But that's why we keep it limited to two populations. You're comparing a pair of populations. This is the best way to do it. When you have more populations, you need to do analysis of variance, which hopefully we'll cover on Thursday. So we will continue now with hypothesis testing for two populations. It will be the same thing as we did before. We're going to take a test statistic that summarizes the properties of these two populations based on what we've observed. And also we've done that with confidence interval. We're going to take that test statistic and see where it lies on the normal distribution or the t distribution or the f distribution for variances, and figure out if it's outside the rejection region or inside it. Okay? It's the same procedure, the same mechanism. What changes are the test statistics. Okay? And I will give you also a nice summary sheet once we're done with this, similar to the one for confidence intervals, to summarize everything. Okay, so we will start with a known population, known sigma for the populations. Okay, so sigma 1 and sigma 2. And again, with the null hypothesis, with the hypothesis testing, we follow the same procedure. Say the null alternative, determine which distribution to use. You know, do we need normal if we know sigma, or proportions? We use a t distribution. If we don't know sigma, we use an f distribution in this case when we are comparing variances. With a single population, for variances, you use the chi-squared because it was simply a variance. For two populations, we have a ratio of variances, so we need to use what's called the f distribution, if you remember, when we did confidence intervals. Okay, and then you gather the data, calculate the sample statistic, and draw a conclusion based on that sample statistic and your level of significance. So starting with when we have two populations and we know their standard deviations, we're going to pick a sample from each population. Now, these are unpaired. They're independent of each other. We'll address the situation with paired in a little bit. But when they're unpaired, you know sample 1 from population 1 and a sample from population 2 here. They called it X1 and X2. That's what they use in the textbook. But we can use X and Y. So X is from population 1, Y is from population 2, let's say. So X bar, 1 bar, X2 bar, or X bar and Y bar, they are the sample means from population 1 and population 2 respectively. Mu1 and mu2, now that's going to be where our null hypothesis is. Okay, so when we did a single population hypothesis test, we had an assumption on the population mean. Now we need to have an assumption. We need to know the population means separately. All we need to make an assumption about is their difference. And most of the time, the null hypothesis is going to be before treatment, after treatment, there's no difference. So mu1 minus mu2 is 0. Okay? Most of the time, our null hypothesis is going to be a statement that mu1 minus mu2 is 0. In some other cases, it's going to be mu1 minus mu2 equals some value. Okay? But that's going to be our null hypothesis. You don't need to know or to make a null hypothesis about population 1 separately than population 2, just about their difference. So think again about my treatment of the radon. Before radon and after radon, my null hypothesis is going to be it didn't change the mean value of radon levels. Therefore, mu before minus mu after is 0. I don't need to know what mu before and mu after is. Okay, all I need to know is make a statement is about that difference. So that's an important thing that adds up to the complexity as you go to more populations. Sigma 1 and sigma 2 and n1 and 2 are variances of population 1, population 2, and n1 and 2 the sample sizes from population 1 and from population 2. And once you get this z statistic, you're done. You're only working now with a single distribution, which is the normal distribution. Okay, and you see where that your z statistic lies within the rejection region. Are you inside or outside? You determine the rejection region based on the significance level, and the significance level is going to give you the critical values in the case of the normal distribution, you have a minus z for a left-tailed test, a plus z alpha for a right-tailed test, or for a two-tailed test, you have two regions split in half, alpha over 2, and so minus z alpha over 2 and z alpha over 2. Or you can use a p-value. Again, same exact procedure. The only thing that's different is this, how you calculate your sample statistic. Okay? Once you have your sample statistic, you're done. Everything else follows as before. Okay? So we'll start with an example and then build the spreadsheet based on that example. We do it for a left-tailed, right-tailed, and two-tailed in one shot, and then we can just simply apply it on the examples. Okay? A university researcher is interested in a new instructional method of English for university freshmen whose scores require them to complete remedial work. He is comparing the traditional two-semester instruction against the new one-semester co-requisite instruction. He wants to test the claim that students who are in the traditional English remediation sequence score lower on the departmental final exam in English composition, score lower than their counterparts in the new single semester co-requisite class. Okay? So that's his claim, that they score, the ones who take the traditional, they score lower than the new class. 93 randomly selected students were chosen for the study, gives us our chosen for the study. Of this group, 41 were randomly chosen from the group who took the traditional remediation, so that gives us one of the population sample. We haven't decided which one is going to be population 1, which one is going to be population 2. So 41 goes to either N1 or N2, and this group scored a mean of 66.47, so that gives us the mean of the first sample. The other 52 students were randomly chosen from the new one-semester co-requisite English classes and scored a mean of 69.43. So that gives us N2, 52 students, and the other mean for the other sample. Assume that the population standard deviation for students in the traditional English class is 8.05 for score points on the exam, and the population standard deviation for the students in the co-requisite course is 9.22. Test the claim using a 0.1 level of significance. Okay, so what statement are, this researcher is claiming that the students in the new co-requisite course, they score, the students in the traditional one, they score less than the students in the new approach. So he's making a claim that, so let's call population 1 as the traditional remediation course and population 2 as the new co-requisite course. So he's saying that mu1, or the average final exam grade from that population, is less than the final exam grade, the average final exam grade from the new course, the new approach. All right? Now, so that gives you the claim or the research hypothesis. Therefore, automatically you'll infer that the null hypothesis is that there's no difference between the two. And that's the case for most situations, that mu1 and mu2 are equal. I don't need to know mu1 or mu2 or the claim about the population, just that their difference is 0. Yeah?
So is that going to be just how we're phrasing approaching this class?
Yes. And it will be worded so differently in different books, in different contexts, right? But all you have to do is, that's the hard part. You have to translate it to this kind of statement. Typically, I find it easier to identify the alternative hypothesis and then go back. If the alternative hypothesis is saying that they score less, the null hypothesis it means that there's no difference, or they score more, right? But we're only making equal statements in the course so far, okay? So the null hypothesis is whatever the alternative hypothesis is not, really, okay? And so we can summarize this like this. So we'll start with we'll call population 1 as the traditional two-semester remediation, and population 2 as the co-requisite English, the new course. The null hypothesis is that there's no difference in the mean final score between these two populations. And the researcher is claiming that the population in the old approach scores less than the population in the new approach. Okay, that mu1 is less than mu2. Now we have these numbers, x bar for population, for sample 1, 66.47, sigma 1, N1, and y bar, sigma 2, and N2. Notice I used y bar over here. It's the same as x1 bar or x2 bar. I prefer to use the x and y notation. Okay, so let's come back here. Sorry. Okay. Let's grab the Google Sheet, so hopefully the recording didn't get cut off. We'll see. Okay. So let's grab our, oh, wow. Okay. That zoomed in quite a bit. Okay. So I'm going to create a new Google Doc and a new spreadsheet. Yep, new Google Sheet. I'm going to keep it next to the other one because I'm going to copy some of the stuff from over here because they're going to be, all of this is going to be the same. We're just going to add some more, a bunch of more numbers over here, okay? So let's call this hypothesis testing two populations, okay? Go away. All right. Now let's zoom in a little bit. And here's how I'm going to do this. For sample mean 1, so sample, let's just type them in, sample mean 1, so that's for population 1. So in this case, it's 2.9, or no, what was it? Let me get my numbers. It was 66.47. And again, these numbers will change for different problems. And then we have my standard deviation for population 1. So SD1, or standard deviation 1, or yes, SD1, or SDDev1 for, so this is a known sigma. Actually, let's call this here known sigma. Okay. And in this case, we had, what, 8.05. And N1, or sample size 1, and that was 41. And then sample mean 2, we had 69.43, correct? And standard deviation for population 2, not sample 2, for population 2, because we know it, it was 9.22. We assume that we know it. And N2, sample size 2, is 38 or 52. 52? Yes, 52. Okay, now my null hypothesis, H0, or in other words, mu1 minus mu2. Okay, because in these statements, in the z statistic, I have x1 minus y, x minus y, right, and mu1 minus mu2. So I might as well just state null hypothesis. Although we said mu1 equal mu2, that's the null hypothesis, it's equivalent to saying mu1 minus mu2 is 0. So I will always use that as my null hypothesis, the difference between the means of the assumed means of the population. So in this case, it's 0. So my H naught is 0. And then my significance level alpha is, we said we wanted it to be 0.1, so 10%. And then finally, I do my sample statistic or test statistic, sample statistic or test statistic. Let's move this window over here. So we had sample mean 1 minus sample mean 2 minus H naught, or mu1 minus mu2 over this guy. All right, so let's program this over here. This will be equal to, so I need two parentheses actually. So we're going to do x1 bar or x bar minus y bar or x2 bar, okay, minus mu1 minus mu2, which is this number over here. And this is going to be divided by square root of sigma 1 squared over n1. So that's sigma 1 squared over n1. And I mean, we could do this in Python. It would be much easier in terms of like defining variable names. But this is nice and handy. You don't have to grab your Jupyter notebook for simple tests like this. So I think it's easier doing it this way, plus standard deviation 2 squared, because that's the variance, over n2. Okay, close parentheses for the square root, and that gives us our sample statistic. Okay, and it's a negative value, minus 1.65. Now, indeed, this example is a left tail test because the claim is that mu1 is less than mu2, or mu1 minus mu2 is a negative value. So, having the the sample statistic to the left is kind of consistent with what we're trying to accomplish here. So it does show that there is a change, a possibly lowering of the mean value, but we don't know if it's statistically significant, if it's enough. Okay, so now what I want to do actually is copy and paste everything I did here, but I just need to adjust the numbers a little bit, okay? The cells a little bit. What happened here? What? Okay, 125. Okay, so I'm going to copy these guys and just throw them in here. Let's zoom out a little bit, maybe 100%. Oh, nope, that's bad. Okay. So I'm going to put these here. Now, these are going to be not a number because I changed the values over here, whatever was going on here. So all I have to do is come and put in the correct values over here. The critical value is always based on the significance level, because that's going to give us the z value such that the area to the left is alpha, or the area to the right is alpha, or to the left and the right is alpha over 2. Okay? So in the previous spreadsheet, this was B5. Over here, it's B8. Okay, so I have to do is just do B8. Now, I don't know what it is on your spreadsheets. Maybe you had a few more rows. Just figure that out. Okay? So this needs to point to this alpha over here. And since I'm at it, I'm going to fix the right tail one as well. This will be B8 as well. And this one is going to be B8 over 2 in my spreadsheet. In your spreadsheet, it might not be B8. Okay? I don't know where your alpha is on your spreadsheet. All right. So now my p-value is based on my sample statistic. Okay? So my p-value is going to be based on this one over here, okay? And this guy is going to be based on this one over here, okay? And finally, this guy is also going to be based on my sample statistic, which is over here. Now, the rest is the same, well, except for this. So this is saying if this p-value is less than my significance level, so which is B8, or alpha. Sorry, let me zoom in a little bit. Let me zoom in a little bit here. Okay, this is better. Okay. So for the conclusion, before we do the error and confidence interval, let's just get up to this point. For the conclusion, if my p-value, which is this guy, is E3, is less than B8, which is my alpha significance level, right? Then we reject. Otherwise, we don't reject. Same thing for this one. Here, it should be B8. We're comparing F3 to B8. Okay? And finally, this guy is also comparing G3 to B8. Okay? Now, in our test, in our example, we are here on a left tail, and it says that we actually will reject the null hypothesis, that we do observe a difference, and the means are not the same, and indeed, the means of the mean scores of the students in the old way is actually less than. We have sufficient evidence to say that this new course is making a difference, is increasing the scores of the students. Okay, so you're still stuck here. I can go to whatever cell you want. Pardon me? E3, this one. Yeah, so it's the same stuff we had in the single population hypothesis test. Same stuff, except here we have a few more rows because we have two populations. right? So the reference cells have changed a little bit. And this is a good exercise to know, to remember what you're calling, okay? So this is what I will test you at. Like when we do the critical value, is it the area to the right of the sample statistic or of the alpha, right? So, we good? Okay. You better iron out these spreadsheets because you're going to be using them in your exam. Yes? Yeah. Okay. So let's see what I have here, if I'm consistent. So my spreadsheet says we reject. I'm just comparing two populations. Okay, blah, 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 blah. And indeed, we do reject. Yes. Okay. So that's the critical value. That's my sample statistic. We are in the rejection region. So we're going to reject. Good. Okay. So that's it. This is a left tail test. We can do a right tail test or a two tail test. So maybe we do one more example. Actually, let me do this next example because this is the only example I've seen where we break that null hypothesis equals 0. It's a little bit of a word salad. It took me a minute to even comprehend it. But before going there, let's do the confidence interval. So similar to what we did with a single population, now your textbook doesn't do these confidence intervals, okay? I'm just adding them in the slides. So, just you won't find them in the textbook. So just fall back on the slides or the spreadsheet to get these confidence intervals. But similarly to what we did with a two population confidence interval, we're saying that X bar, the true population difference is the true difference in population means is between X bar minus Y bar plus or minus that critical statistic value, that Z value, times square root this formula for the combination of the variances, okay? Now, this should work straight out of the box over here because we've had this already programmed. Actually, no. Yeah, so here we need to change this formula, actually. For the confidence interval, so let's change it since we're at it. This a little bit here. Okay. So I have X bar minus Y bar plus or minus critical value times square root of sigma 1 squared and 1, etc. Okay. So what I have here is the formula for a single population error interval. Okay. So what I need to do now is do it for these two populations. I already have the Z star value, and I take the absolute value because I want the error to be positive, and then I can manually add or subtract. And so this would be a square root of sigma 1 squared, which is this one, squared over n1 plus sigma 2 squared over n2, okay? And that simply gives me the error. Okay? That should give me the error. Same thing over there. I need to copy and paste this over here. This actually, for the right tailed, it should be the same value. It doesn't matter. But we'll just paste it over here as well. So we can put F2 over here if you want. It will be the same exact value. For the two tail, okay, we have to put this value over here, G2, okay, because it's based on alpha over 2. And that immediately gives you the confidence interval for a single tail or for a two tail test, okay? So this tells you your true mean is between, the true difference in means is between these two values at the significance level of 0.1 or confidence of 90%. Okay. So now this is an interesting one. It took me a minute to comprehend, so I'll try to go through this slowly, and then we'll skip the right tail test. So a drug manufacturer claims that its new cholesterol drug, when used together with a healthy diet and exercise plan, lowers a patient's total cholesterol level by over 20 points more than simply changing diet and regimen. So we already have a benefit of just simply, if you do diet and exercise, you get a benefit. But here they're saying it's not only going to lower the points, it's going to lower by more than 20. So they're giving me that 20 to indicate the difference already. Okay? So to test the claim, a sample of 55 patients with high cholesterol is chosen at random from a cardiologist's list of patients to take the drug, in addition to changing their diet and exercise plan. So they tell all of them, change your diet, as if that's possible, an exercise plan, change your diet and exercise plan, and some of them are going to take the drug, okay, and then we're going to compare. Okay, at random, etc. So in addition to changing their diet and exercise, over the course of 3 months, this group lowers its total cholesterol level by a mean of 44.7 points. The population standard deviation for this group is known to be 6.8 points. Another 55 patients with high cholesterol only changed diet and exercise. So the other guys, the first 55, they changed diet and they did exercise and they took the medicine. Another 55 patients with high cholesterol only changed diet and exercise, okay? And they lowered their levels by a mean of 23 points, okay? So these guys lowered by 44.7, these 23.1. Okay, now the population standard deviation for this group is known to be 5.3 points. That's the manufacturer's claim using a 0.01 level of significance. So here it's a little bit interesting that more than 20 points is kind of what throws a wrench in what we're thinking about. Okay, and not only that, the way we're going to approach this is as follows. So we're going to let population 1 be the patients who take the drug, and population 2 be the patients who do not take the drug. Now, the manufacturer is claiming that its drug lowers cholesterol by over 20 points more than diet and exercise. Now, notice that the means that are being reported, they represent the amounts by which the patient's total cholesterol is lowered. So when I say the mean value is 34, that's not the total cholesterol, that's how many points it's been lowered. Okay, so that's the actual number of points by which we lowered cholesterol. So in other words, they go take the blood test, they measure their cholesterol level, they measure how much they lowered it from before doing the regimen, and they report those values as just positive numbers, but this designates the number of points that they lowered the cholesterol by. Okay, so just watch out for that. I don't think I want to make it this complicated. This seems like too tricky, frankly. Notice that the two means being tested represent the amounts of the patient's total cholesterol. Hence, for each population, mu refers to the mean number of cholesterol points lost. Now, mathematically, the researchers' claim is that mu1, so those who take the drug, is actually greater than mu2 plus 20. So in other words, if you take the drug, remember mu is the number of points you lowered your cholesterol on average. It's saying that if you take the drug, you're going to lower it by as much as the other population plus 20 and more. So more than that. Okay, so it's sometimes easier to do the claim, the alternative hypothesis, to recover the null hypothesis. So this automatically means that the null hypothesis is the opposite of that. In other words, that mu1 minus mu2 is 20 or less, actually. But we'll cap it at 20 because we're just doing equal statements here. Okay? Does this make sense? Not a lot. Okay, well then you read it at night and enjoy understanding it. But once you get to this point, then it's just only math. Okay? But this is the critical value. Two things. To realize that the means are reporting the cholesterol points lost. So the claim is that the population that takes the drug is going to lose more points than the previous, more points than the other population, and more than 20 as well. So we're going to lose more than mu2 plus 20. Okay? If they didn't put that 20, if they said just more, then we would be mu1 minus mu2 equals 0, and then the other hypothesis would be greater than 0. Okay, so throwing in that 20 is the only thing that changes here. Okay, so now we can just punch these numbers in our amazing spreadsheet. Okay? So sample mean 1, let's come back here, see if I might have a summary here for you. Okay, so we're going to say population 1 is patients taking the drug. So this is going to be my X bar, and it's 44.7. Standard deviation is 6.8 points, and N1 is 55. My sample mean 2 is 23.1, and my sigma 2 is 5.3, and my N2 is also 55. Now, my null hypothesis is mu1 minus mu2 is what? 20. That's where my null hypothesis changes, and we want to test this at 0.01 level. Okay, and now this is a two-tailed test. Actually, no, this is a right-tailed test, so we're going to fail to reject the null hypothesis. Okay, in other words, yeah, there's no difference. Diet and exercise better than drugs. Now, if there was a drug that made me exercise while sleeping and just lose weight, that would be great. But yeah, nothing replaces diet and exercise. Okay? All right. On and forward. There's another example about a two-tailed test here. So you can, it's in the slides, and you can figure it out yourself. It's about two universities who are competing with each other, et cetera, and you do the hypothesis testing. Okay. Now I want to jump to the next level of complexity is when you don't know the population standard deviations. We did this with confidence intervals, and we had two situations. We had a situation where really we don't know what they are, we don't know if they're equal or not, and we used one formula, which was based on the t-test. But there was another special case when we assumed that the populations have equal standard deviations. That helped us tighten in our estimate, and we used what's called the pooled approach. You don't have to do that. The t-test is sufficient, but if you want more accuracy in your results, you should use the pooled approach. All right, so when you don't know the population sigmas, we estimate those with the sample variances, but instead of using the normal distribution, we've added more uncertainty here because we use sample variances to estimate population variances. So we introduced the chi-squared effect, if you want, into our analysis. So instead of using a normal distribution, we use the t-distribution. It has a little bit more uncertainty, so it compensates for those errors. Now, in this case as well, remember, similar to what we did with confidence intervals, exactly the same thing. We're going to use a t-distribution, and the t-distribution requires degrees of freedom. Okay, and then number of degrees of freedom of the distribution test is given by the smallest, so the minimum of n1 minus n1 and n2 minus 1. Okay, because we have two samples, we pick the one that is going to give us the most uncertainty to be as conservative as we can in our analysis. All right? So similar to what we did with confidence intervals. Now, when the standard deviations are assumed to be equal, you still don't know what they are, but you assume that they're equal because they're coming from the same group, maybe same students, etc., same professor, same department. So you might assume that standard deviation are equal. You don't know what they are. Then you use the pooled approach. Gives you a little bit more accuracy. It's still a t-statistic. So it's just still a number. This could be this one or that one. You just have to make a decision which one to use. But in this case, the t-distribution is going to use, this pooled degree of freedom, n1 plus n2 minus 2. Okay? Now we can program this all in Python, which is easier. We can also program it in Google Sheets. So let's go ahead and do that. We'll start with one example. And again, obviously, the same applies for rejection regions and p-values. The t-distribution, remember, is symmetric, so it's the same approach as we did before and with the normal distribution. All right, so we start with this example and then build the spreadsheet. Suppose that the Smith CPA, a certified public accounting firm in Chicago, claims that its clients receive larger tax refunds on average than clients of its competitor, Jones and Company CPA, located on the other side of Chicago. To test the claim, so we're saying, suppose it claims that it receives, so Smith says, my clients receive larger tax refunds than clients of Jones and Company. To test the claim, 15 clients from the Smith firm are randomly selected and found to have a mean tax refund of $942 with a standard deviation of 103. So now this is the standard deviation of the sample, not the population. Okay? If it were for the population, we would say all the Smith CPA clients have that standard deviation. This is just for this sample of 15 clients. At Jones and Company, a random sample of 18 clients are surveyed, and their mean tax refund is $898 and standard deviation of 95. Test the claim made by Smith firm at the 5% level of significance. And obviously, because we have 15 and 18 clients, so in each case it's less than 30, we have to assume that the population distributions are approximately normal. So for the tax refunds of Smith Company and the tax refunds of Jones Company. Okay? So now the null hypothesis is saying, before you start with the null, I start with the claim. It's easier for me to start with the claim that Smith Company, they have a larger tax refund. So if we call Smith Company population 1, then mu1, the mean tax refund for Smith Company, is greater than the mean tax refund of Jones Company. Okay? If the null hypothesis, therefore, is the other side of that, or in other words, there's no difference in the mean tax refund, or it could be less. Okay, but we're just going to put an equal sign. Okay, so in other words, this is my claim for the null and alternative hypotheses. Population 1 is going to be the Smith Company. Population 2 is going to be Jones et al. If as far as we know, they get the same tax refund. But the Smith folks are claiming that no, on average, their people get a higher tax refund. So we'll start building this spreadsheet. We have about 10 more minutes. I think we got enough time to do this. So what I will do, I'm going to duplicate this form over here, this sheet. I'm going to say duplicate. Okay, and we're going to say unknown sigma. Okay, known sigma. Okay, now I have to add a few things over here because we are dealing with a t-distribution. So I'll keep the sample mean 1 as the same. So let's punch in the numbers since we're at it. Here are the numbers. Whoa. Okay. So for the population 1 is going to be 942. Let's shrink this guy. Population 1 is $942. And sigma 1, so I'm going to call this S1 rather than standard deviation 1. This is the sample standard deviation, just to make sure, you know, this actually should be S1. This is my bad. Bad, Professor Saad, bad. Okay. You should deduct points from my exam. Okay. S1 is $103, and N1 is 15. Sample mean 2 is $898, and S2 is $95, and N2 is 18. Now my null hypothesis is that there's no difference between the two, and we were at the 5% significance level, so 0.05. Now this is going to change here. All the numbers are going to change as well, but let's just fix this for a second. So for my sample statistic, I need to be able to switch between these two formulas. So I need an option to a toggle switch or like a checkbox to say known sigma or unknown sigma. Okay? And furthermore, I need one other variable to refer to the degrees of freedom, because in this case, the degrees of freedom is n1 plus n2 minus 2. In the other case, it's the minimum of n1 minus 1 or n2 minus 1. So if I do that in one variable called degrees of freedom, then when I go up there and call the t distribution with the degrees of freedom, I don't have to reason about this. I just call degrees of freedom. Okay, I use the cell for the degrees of freedom. So I need at least two more cells here, and that's going to be equal sigmas assumed for the population, and this would be equal to a, let me see, a toggle or like a checkbox. Let me see, how did I do it? Checkbox, hold on. We can go here and ask Google how to do a checkbox, insert checkbox. There you go. So if I press this now, this is true or false, okay? And I need degrees of freedom, or DF, degrees of freedom, or degrees of freedom, DOF. And this is going to say, if I have equal sigmas, then my degrees of freedom is n1 plus n2 minus 2. If otherwise, so not unequal sigmas, is going to be the minimum of n1 minus 1 and n2 minus 2. Okay? So see the difference? If it's equal sigmas, it's going to be n1 plus n2 minus 2. If it's unequal sigmas, my degrees of freedom is 14. Now this is cool because I've isolated all the decision making into these two cells here. Now when I go up to calculate the critical value and pass on the degrees of freedom, I don't have to make the reasoning over there. This is already parentheses within parentheses. All I have to do over there is say call degrees of freedom. It's like in Python, you compute the variable, store it, and that's it. Okay? Okay, so now we can go to critical values. Now, excuse me. Yeah, so if we're saying if we have equal sigmas, then use this formula n1 plus n2 minus 2. If we have unequal sigmas, it's the minimum n1 minus 1 or n2 minus 1. Oh, I made a mistake here. Should be n2 minus 1. Thanks, everyone, for correcting me. It looks like it didn't make a difference because the minimum was still on the first cell. Okay. We good? All right. Now let's jump to the critical values. Now, obviously, here we need to switch to a t distribution instead of a norm.s.inverse. So I'm going to do, so the critical value is going to be the t-score such that on the left tail is going, the area to the left is alpha, right? So I need to do t.inverse, okay? And then I'm going to give it the probability to the left, alpha, and the degrees of freedom. There you go. I already have the degrees of freedom. I don't have to make a decision up there in this cell about which degree of freedom to use, if and whatever, right? I already have it computed down here. Okay? Bam. Okay. So now, so this is a left, for the left tail test. Now, in this example that we're doing, this is a right tail test. So this is not gonna matter for us, but let's do the p-value anyway. So now for the p-value, we need to use the regular t-dot distribution. So t-dot distribution on the left tail, it needs a t-value, number, degrees of freedom, and whether it's cumulative or not. So for my t-value, I need to give it my sample statistic. Remember, the p-value is the area to the left or right of your t statistic, okay? Of your sample statistic. And degrees of freedom, we have that already, and this is going to be cumulative. Okay? So that gives me my p-value for a left-tailed test. For a right-tailed test, we're going to have to do something similar. Now, fortunately for the t-distribution, we can either, so I can either copy this one here. The critical value on the right tail, okay, so let's try one thing. T dot inverse, so this is equal T dot inverse. Okay, so now for the right tailed, I want to find the critical T value such that the area to the right is alpha. Because this is symmetric, I know it's going to be 1.76. Okay, so I can take the absolute value of that, will be fine. Or we do it another way and say, well, the area, because the T dot inverse only is computing based on area to the left, so I need to do 1 minus my alpha here, right? And then degrees of freedom, and then that would give me, there you go, see 1.7613, which is because of symmetry, okay? Similarly, for the p-value, here we use a t-distribution. This is based on area to the left. So the p-value for the right tail is the area to the right of my sample statistic, okay? So this would be a t dot distribution. But look, here I have a right tail distribution, so I don't have to worry about 1 minus and whatnot. So I'll just use the RT to give me the area to the right, and I give it my sample statistic and the degrees of freedom. Okay? And that gives me 0.113, all right? And that is going to be grounds to fail to reject the null hypothesis. Now, you could have based this on a rejection region because my sample statistic is 1.26, and that's less than 1.76. So we are outside the rejection region. So we're going to fail to reject the null hypothesis, okay? So if we go back here and see this visually, okay, if we see this visually, our sample statistic is 1.26, but the critical value is 1.76 and higher. Okay, so that's my rejection region. My sample statistic is here. So we're going to fail to reject the null hypothesis. What was our hypothesis that, what we were doing? Oh yeah, the CPA. So you know what, they get about the same tax refund. We don't have enough evidence to say that Smith CPA is getting a larger tax refund than the other guys. Okay, so you can go uptown, downtown, doesn't matter, you're going to get the same tax refund, okay? All right, we're done. Thursday, okay, we'll finish this off and hit ANOVA, okay? Godspeed. Tuesday, we left off doing a two population test with an unknown sigma, and we did, I think, a right tail distribution. We did the spreadsheet, and with the spreadsheet, if you remember, we had this really nice conditional here. If you assume you have equal sigmas, then you change your degrees of freedom, and then your formulas would change accordingly based on whether you're pooling things or not. And based on that, we were able to compute our, well, actually, we didn't finish here, right? We were not done yet over here. Correct? So I think we left off just putting this here and putting the conditional on the degrees of freedom. So let me remind you of what we were doing. So this situation was comparing two populations with unknown sigma. Unknown sigma immediately implies a t-distribution. Okay? And we had two situations. So the first situation is if the sigmas, if you assume nothing about the standard deviations of the populations, if they're not necessarily equal, then you would use this t-statistic, which is similar to the single population t-statistic, except now you have two populations, and x bars are the sample means from population 1 and population 2. We call them x bar and y bar as well. Mu1 minus mu2 is your null hypothesis. So it's always easy to define the null hypothesis for two populations based on the difference. You don't need to know the mean, make a hypothesis on the population 1 and population 2. All you have to say is a statement about their difference. They're not different, or if they're not different, then mu1 minus mu2 is 0, or mu2 is 10 is mu1 plus 10, something like that, right? But typically that mu1 minus mu2 is 0. Your null hypothesis is there's no difference between the population taking drug A and taking drug B. So mu1 and mu2 is, you assume it is 0, and then you try to reject that. Now, when you assume that the standard deviations are equal, you use the pooling method, and with the pooling method, your t-statistic changes a little bit, okay? Let me see if we did we do that here? I think we did. Hold on. I think we did. No, we didn't. Okay, good. So, and last time I told you, I don't want a spreadsheet for unequal sigmas and another spreadsheet for equal sigmas. I want to build these together in one spreadsheet. And there's another kink in this, is that the degrees of freedom when you're using the unpooled method, when sigmas are not assumed to be equal, the degrees of freedom is the minimum of n1 minus 1 and n2 minus 1. n1 is sample size 1, n2 is sample size 2. But in the case of the pooling method, where sigmas are assumed to be equal, your degrees of freedom is n1 plus n2 minus 2. And so, that throws another wrench in the plan. And what we sorted out last time is figuring out the degrees of freedom. Instead of having to do the logic about whether the sigmas are equal or not equal, instead of having to do that logic over here inside the critical values, so when you have to put in your degrees of freedom, right, we just passed on a degrees of freedom, and we'll have the degrees of freedom being calculated over here based on this checkbox. So if you have equal sigmas, it's going to pull them together. If you don't have equal sigmas, it is not going to pull them together. Okay. Now the next step is figuring out the t-statistic, and with the t-statistic, hold on, with the t-statistic, we have to this is the other if statement where we have to consider whether we have equal sigmas or not. Now this spreadsheet is copied from the spreadsheet for a single population, okay, or the spreadsheet from the z-values. So the only thing that's changing, actually, the spreadsheet from the single population t-test. So the only thing that's changed here is how we're evaluating the sample statistic. Everything else does not change and remains the same. So all I have to do now is figure out how to embed these formulas into the spreadsheet. So let me move this. And I don't know if I should just give you these spreadsheets without explaining this next year, but I think because you're not technicians, right? A technician would just learn, use this spreadsheet if you're doing this, use that spreadsheet if you're doing that. You're more than that, so I feel like it's important to do some of the work together so that you learn what you're doing. All right, so let's do this together. I need to program this formula. Now, if my sigmas are equal, then I'm going to do this. Otherwise, I'm going to do this formula. Okay, so let's start with this guy here. And move this here a little bit. We'll zoom in a little bit here. So what I'm going to do is, say, put an equal sign. Now, obviously, in Python, this would be tremendously easier. I'm going to do if b10, this thing, if this is true, therefore I have equal sigmas, then my test statistic is going to be this formula. So what I'm gonna start with the numerator. I have x bar 1, which is sample mean 1, minus sample mean 2, okay, minus, what is mu1 minus mu2? It's my h naught here, this one, correct? B7 is mu1 minus mu2, right? So we sorted out the numerator. Now for the denominator, we have two square roots, a product of two square roots. The first one, again, we're going to do a numerator. So we have n1 minus 1 times standard variance 1. So that's s1 squared, okay, plus n2 minus 1 times s2 squared. Okay, So all of that is going to be in the numerator. So let me just check. All right, so this is, yep, so that's going to be in the numerator. So I need one more parenthesis here. All right, see what we're doing? So this is the numerator divided by another pair of parentheses, n1 plus n2 minus 2. Oops. Okay. Now, I still have another square root, 1 over n1 plus 1 over n2. So what I do another divide. So divide by square root, divide. So full numerator dividing by the first square root, dividing by the second square root. That's the equivalent of this formula. So another divide is going to be square root of 1 over, so 1 over n1 plus 1 over n2. Hold on, 1 over n2. Okay, so let me expand this for a bit. Okay. It gave me false. Okay, false because, yep, we're not doing equal sigmas. All right. Now, when the sigmas are not equal, we have to use the other formula, which is the simpler formula. Okay. And that's equal to, again, with the numerator, I'm going to do b1, mu1, or sorry, x1, x bar 1 minus, or x bar minus y bar, minus the h naught, the null hypothesis, okay, divided by square root, open parentheses, and what do I have here? S1 squared over n1. So we got S1 squared over n1 plus S2 squared over n2. Okay? And I think I need to close this with a one more. Yep, there you go. Whew. Perfect. Okay. Okay, so let's run the example. Go back to the example. This was the Smith CPA company saying that they save on average $942 with a sample standard deviation 103, but the Jones company found to have a mean refund of $898 with a standard deviation of 95, and test the claim that the Smith firm saves more for its clients, for their clients, at the 0.05 significance level. Okay, so if you remember, we had this null hypothesis that the average saving for Smith company is equal to the average saving for the Jones company. In other words, mu1 minus mu2 is 0. There's no difference in the average saving. The alternative hypothesis is that the Smith company saves more on average than the Jones company. Right? So it's a right-tailed test, and if you do this with this statistic, then for a right-tailed test, you're going to fail to reject the null hypothesis, and therefore their claim is not valid. They're probably not saving much more. Okay? Now, if you had assumed that the samples are equal from the population, then you would check this guy. It still fails to reject, but it changes your statistics, right? Changes things a little bit. In this case, it is not sensitive to that. But there's another example where you have to use the pooled approach here. In this example, you do that at home. Assume that the variances of the populations are unknown, but assumed to be equal. Okay, so then in that case, you run it through the spreadsheet, and you can get the answer, and you can compare your answer to what I have over here and also in the textbook. So you have to do these things. It's just a lot of practice exercises. These are lifted out of your textbook. There's a couple more examples maybe in your textbook, so feel free to do those. Now, for paired data, this is an easy one. Why? Because when we have the data paired, what did we do last time for confidence intervals? Took the difference and we treated that as a single population confidence interval. What are we going to do here? We take the difference and we treat that as a single hypothesis test on a single population, which is the population of the differences, right? So fairly easy. What you do, you take the numbers and plug them in our calculator for a single population. So I have everything detailed here for you. I'm not going to cover this in class because it's a degenerate case. So no offense to the case, but in mathematics, degenerate, it means like a simple case. It's a simple case. So, but note here that you have to use a t-test because we do not know the population standard deviations. That's always assumed for paired data, okay? I have a little example over here. Again, 2 examples also from your textbook. Now, on to proportions. And I know we haven't covered much of proportions. It's not a big deal, but occasionally you'll see a proportion here and there. Similarly, for proportions, as we did before, because they are represented by a binomial distribution, and the binomial distribution is the approximation for a normal distribution. So yes, we are normal, and essentially you would use a z-test in proportions. So we go back to the normal distribution and the z-test, except now your z statistic is a little different. Instead of x bar minus y bar minus the null hypothesis, now you're looking at proportions. The unhatted p's, remember, those are population proportions. So P1 and P2, they're not probabilities. They're what you believe about the proportions. Like, 40% of students at the University of Utah eat at the Union. Okay, that's a claim about proportion, or 40% of or there's no difference between freshmen and juniors in eating habits at the Union, right? So that would be a statement about the population proportions. But then in your samples, you might find that 30% eat and 40% from freshmen and 40% eat from the juniors. Okay, so this is what you have to factor in now. To use this test, you have a few conditions that you need to satisfy. Coming from the binomial distribution. For a single population, it was easy. We only had 2 conditions. For 2 populations, we have 4 conditions that we need to satisfy. And they're listed up there, n1 p hat 1 greater than 10, and n1 1 minus p hat 1 greater than 10, and so on, n2, and so on for n2 and p2. Okay. There's one little thing here that you have to keep in mind is that there's this thing here called p bar in the denominator. We've never seen this p bar, but this p bar is sort of a grand, what we call like a grand mean. It's essentially your sample values over, so x1 and x2 are the sample values that you drew out of the population. So let's say you picked up 50 students and 20 of them eat at the cafeteria, then x would be 20. Okay. Now n1 and n2 are the sample sizes. So we'll program this in a spreadsheet together, and then the rest is a typical hypothesis test. So we'll start with this example. The mayor's chief of staff thinks that a local newspaper article has changed the community's opinion about the mayor. To test this theory, this hypothesis, a theory is actually when a hypothesis has been corroborated with evidence. So you don't say the theory of gravity, not the hypothesis of gravity, right? Or the theory of evolution, not the hypothesis of evolution. So this is really a hypothesis. So people use this very loosely. But always they say, oh, I have a theory about what's going on. No, you have a hypothesis about what's going on. Correct yourself, sir. So anyway, to test his hypothesis, he finds a poll of the mayor's approval rating that was taken before the article came out, and compares it to the mayor's approval rating after the article. Okay? Before the article ran in the paper, 480 out of a simple random sample of 1,200 voters thought the mayor was trustworthy. After the article, 550 out of a simple random of 1,180 voters thought he was trustworthy. So things changed before and after. Based on these data, use a 5% level of significance to test the chief of staff's claim that the mayor's approval rating has increased. Okay? And so our null hypothesis is that there's been no change in the population proportion that believes the mayor is trustworthy. So P1 is equal to P2, or P1 minus P2 is 0. You know what? It's the same. Approval rating is just kind of didn't change. However, now the claim of the staff is that after the article, the proportion of people who believe the mayor is trustworthy has increased. In other words, P1 is less than P2, because we chose population 1 to be the voter's opinion before the article was written. Okay? So the claim is that the number of people, or the percentage of people who believe the mayor is trustworthy before the article was written is less than the proportion of people who believe he's trustworthy after. You can switch that. You could say P1 is the people after the article and P2 is before, and then that sign would change and it would be a right-tail test. You'll get the same result, okay? You'll get the same result. So let's go ahead and program this into our spreadsheet. So we're going to create a new sheet and call it proportions. So let's just add a fresh sheet, start from scratch, and proportions. Okay. And what we need here is, so when you're given data, sometimes you're given a proportion. Sometimes you're given these raw numbers, 480 and 1200. You always need the numbers N1 and N2. Sometimes you're given a proportion and N1, for example. You might be given 40% out of 1,200 voters, etc. Okay, so let's decide to always choose for our inputs the X values from the sample and the N1 and N2, and then we compute proportions as needed. Okay, so we're going to do X1 here. So in this case, this is what? 480, okay, 480. N1 is sample size 1, which was 1,200. X2 is equal 550. Oh, X2, 550. And N2, what was it, 1180? 1180, okay. So perfect, great. This is the formula that we're going to be working with. Now let's define our null hypothesis, H0, which is P1 minus P2. In this case, it's 0. Oops, 0. And our alpha significance level is 5%, so 0.05. And next, we need to check for normality. So to check that we can, so check normality. All right, so what I'm going to do here, I'm going to put like a yes or no. But before that, I need to calculate these conditions, N1 P1, N1 1 minus P1, et cetera, et cetera. So what I'm going to do here, I'm going to put P1 hat over here, which is the proportion for sample 1. So that would be X1 over N1. And P2 hat is going to be equal to X2 over N2. Right? And I need to calculate this P bar here since I'm at it. So P bar is X1 plus X2. So X1 plus, oops, is equal to X1 plus X2 over N1 plus N2. N1 plus N2. Okay, so that gives me 43%. Okay, what else do I need? I need the sample proportion, P hat. Okay. Let's see what it did here. Okay. So now I can compute these conditions here. N1 times P1. N1 P1 hat, so N1 P1 hat is equal to N1 times P1 hat. Okay, it's 480, great, it's greater than 1. And then N1 times 1 minus P1 hat, that's equal to N1 times 1 minus P1 hat, 720, good. And N2 P2 hat, that's equal to N2 times P2 hat. So I'm building those conditions up there to make sure that I can use normality, okay? And N2 times 1 minus P2 hat, that's equal to N2 times 1 minus P2 hat. Okay, all of them are greater than or equal to 10. And therefore, I'm going to make an if statement over here just to tell me that, yeah, we can use normality or whether we're violating normality or not. If, now this is an and statement. If all of these conditions are satisfied. So I'm going to put all of them together under an and statement. If this guy is greater than 10 and that guy is greater than 10, I'm not using even greater than or equal to be more strict. And this guy is greater than 10. I mean, you can use greater than equal. And that guy is greater than 10. Okay, then type yes. Otherwise, no. Okay, so yes, we are normal over here. Okay, so let me put, we satisfy the normality condition. I'm going to put equal signs, just, okay. Okay, well, yeah, you can follow up on the recording if you're kind of getting late. I need to get to the analysis of variance, so I might just release these spreadsheets to you eventually, because you're gonna need them all for your final exam. Okay. Okay. So now I can calculate my sample statistic. Statistic. Okay, and that's equal to this z value, right? So I'm going to start with the numerator. I'm going to open up a parentheses for the numerator, and then this parentheses for p hat 1 minus p hat 2. Don't change the order because you'll mess up the signs. Minus h naught, my null hypothesis, over square root of t. Okay, and this is where p bar comes in. So p bar times 1 minus p bar, okay, times 1 over n1 plus 1 over n2. Oh, okay, 1 over n2, and then close parentheses, close parentheses. Okay, so it gave me this sample statistic of minus 3.25. Now, for this problem, we're going to be using a z distribution. Okay, so I can come here and just pick up all the conditions that I did here, right? Because those were using a normal distribution. Okay, so I can copy those so we don't replicate the work and just paste them here. I just need to adjust what these values are referring to. So this one, the critical value, is based on the alpha level, right? The significance level. So it needs to be B6 over here. This one needs to be 1 minus B6, okay? And this last one needs to be B6 over 2. Does that make sense what I'm doing here? I copied what we did for the normal distribution hypothesis test, because this is a normal distribution test. The only thing that changed is that z statistic. In other words, if I were to take this z statistic here and just manually plug it in my other spreadsheet for the normal distribution hypothesis test, I'll get the answer. Okay? So what I did here, though, I lifted things from the normal distribution hypothesis test and plugged it in here. Okay? Same thing for p-values. P-values are going to be based on your sample statistic, right? And that's going to be this value over here, D7. Okay, and this one, D7. D7. Okay, and this one is going to be D7. Okay. Now let me see. Did I make a mistake here? Nope. No mistakes. Okay. So let's see what I got here. Okay, so my Z statistic in my spreadsheet is the same as the one in the textbook. Good news, they're correct. And the rejection region is when Z is less than 1, because this is a left tail test. The rejection region is Z less than minus 1.645. Now our sample statistic falls below that, so we do reject the null hypothesis. However, here it's not, because I have the wrong values here. I'm comparing the wrong p-values, okay? So I should be comparing this p-value G3 to what? D7 to, no, I should be comparing this one to alpha over here, B6, okay? So we do reject the null hypothesis, okay? This one should be also to B6, okay? And this one should be also to B6, okay? Right, so yes, your final exam is going to have problems like this. Give you samples, such, etc. Punch them in your spreadsheet, get a number, tell me yes or no. Okay? There's no reason you should get this wrong. Okay? So go, build those spreadsheets, ask questions about them, rehearse them, practice them. It's the same thing over and over again. Okay? Now, what I want to get to is variances, because that would lead us to the bigger subject, which is really more important than all of this. So when we get to variances, remember the F distribution. Now, when we were comparing, when we're doing confidence interval on two population variances, we took their ratio, not their difference. And that ratio was represented by the F distribution. It's named after some sir called Fisher, Ronald Fisher. He, is lifted from the textbook here. And so, he's the dude who came up with the F distribution, and he did a lot of work on analysis of variance, etc. So we did talk about the F distribution previously, so that's taken from a previous slide. Now, in this case, it's really easy, because F statistic is simply the ratio of your two sample variances. Okay, sample 1, sample 2, take the ratio of the variances. So don't forget to square if you're given the standard deviation. And if you remember the F distribution, when we're using it, we need 2 degrees of freedom, df1 and df2, or df numerator and df denominator. So make sure you're consistent. You use the correct degrees of freedom for what you call population 1, and correct degrees of freedom for what you call population 2. Now, the only trick here is similar to what we did with confidence intervals, is that the F distribution is not symmetric. Okay, it's not symmetric. And so you still get a right tail test and a left tail test. So if your F statistic less than your critical F value, then you are out in the rejection region. If it's greater than your critical F value for a right tail test, you're in the rejection region. And if you have an unequal test, where it's called a two-tail test, you split alpha in two. Half of alpha is to the left in the left tail, the other half is in the right tail. And the best way to do a variance hypothesis test is based on a rejection region, not a p-value. We can do it with p-values. It's a little bit more complicated, especially with the two tails. But for variances, we're just going to do a rejection region. If your F statistic is less than your critical F, you reject. Or if it's bigger for a right tail test, you reject. Or if it's in either the tails, you reject. Okay? So we'll start with this example and see how it works in Google Sheets before we jump into ANOVA. A graduate student walking around a large college campus notices that the values of professors' cars seem to have a much smaller variance than the values of the cars owned by students. So like students, they have like Lamborghinis, Porsches, all Toyota Camry, and the professors, they're all like driving like Subaru, Forester, or some whole thing, right? So that's kind of the variance, right? So he observes that there's more variance among students, and possibly, students, they're like at different possibly earning levels. Some of them are working, some of them are not, coming from different backgrounds. So their income level has not kind of equalized yet to a certain extent. And so, he observes that. We'll have to see if, so he notes vehicles ranging from small broken down trucks to Porsche convertibles, while the cars owned by faculty are more similar in style and price. Maybe just Priuses everywhere. That's how I imagine like professors would be driving. To test his hypothesis that the values of professors' cars have a much smaller variance than the values of students' cars, he collects data from random samples of 15 professors and 14 students on the values of their cars and calculates their variance for each sample. The sample variance for the values of professors' cars is about $34,000 square dollars, and the sample variance of the values of students' cars is about $45,900 square dollars. Okay, so this seems to indicate that they have a larger variance, right? 45,000 compared to 34,000. There's a $10,000 spread. It does seem like, maybe he's right. Assuming that both populations are normally distributed, we need that assumption because our sample size is less than 30. We have 15 and 14. Assuming that both populations are normally distributed, conduct a hypothesis test using a 0.1 level of significance to test the graduate student's claim, and does the evidence support the student's claim? Okay, so what our null hypothesis is that there's no difference between the population of students and the population of professors. Okay, so let's represent the population variance of values of professors' cars as sigma 1. So the professor's population is population 1, the student's population is population 2. Forget about the greater than sign for a second here. I'll explain this in a bit. And the claim is, the null hypothesis is that there's no difference. That's the null hypothesis. The alternative hypothesis is that there's less variance in the professor's car values than the students. Okay? So on Tuesday, I told you we've been restricted to an equality statement for null hypotheses. That's okay, but in general, you can relax that assumption because really the null hypothesis is everything that's not the alternative hypothesis. I always like to start with the alternative hypothesis. In this case, professor's variance is less than that. Everything else is going to be the null hypothesis. So really, you can add in greater than or equal sign here. But it's okay, just put it as an equal sign. Okay, but I just kind of wanted to point that out. Like, don't freak out that there's a greater than or equal sign. The alternative hypothesis is everything, the null hypothesis is everything that's not the alternative hypothesis. This is logic, right? So these two hypotheses, they need to complement each other as a total mathematical statement. Okay, so let's go and build this in Google Sheets. Man, this is taking a long time, these Google Sheets. I should just package them and give them to you. All right, let's see. So let's create a variance sheet for variances for comparing, doing hypothesis tests with two populations. So variances. Okay, this one should be a little easier. Sample 1 variance, or S1 squared. In S1 squared, in this case, what was S1? It was 34,057. So 34,057. And sample size 1 was 15 professors, because we said population 1 is 50 is professors. Population 2, we have S2 squared, and that's going to be 45,923. So 45,923. And N2 was 14 students, right? N2 is equal to 14 students. Okay? Our significance level is 0.01. And then our sample statistic is simply the ratio of S1 over S2, right? that's really simple. Now we build our left, right, two-tail. Okay. So we'll build our table, critical values. Okay. So now what do we do for the left tail? For a left tail, we need to find the lower value such that the area to the left is equal to alpha, right? So we need, on the F distribution, we need to find the F value such that the area to the left is equal to alpha. And for this, I'm going to use an F inverse. Where are you? Here. Okay. So here I'm going to use equal to F dot inverse. And this is asking the probability. So in this case, I'm going to give it my alpha value. That's the probability. And it needs degrees of freedom 1, which is n1 minus 1. That's the numerator degrees of freedom. Denominator degrees of freedom, n2 minus 1. Okay? And that gives me my, my sample statistic. Okay. Now, if my critical value. My sample statistic is 0.74. My critical value is 0.26. So my sample statistic is not within the rejection region. So I'm going to fail to reject the hypothesis, okay, that the Professor Scars have. So I'm going to fail to. I'm going to fail to reject the null hypothesis. Okay. So in other words, let me just check. I got my numbers correct here. Okay. Oops, I didn't get my numbers correct here. 45, 9, 23. So my alpha. Yes. So yeah, it should be. Yes, sorry, that's right. So this should be 1 minus alpha. Nope, that shouldn't be 1 minus alpha. This is this. They gave us the significance level, right? Yes, testing at a level of significance 0.1. Sorry. Yep, 0.1. Thank you, Elijah. Okay, there you go. Okay, that makes more sense. But it's still. So we still fail to reject the null hypothesis. So we only rejected if F is less than that critical value, but it's not. So we fail to reject the null hypothesis that that they have equal variance. Okay. Right. So have a smaller variance than the values of the student scores. Hold on. Smaller variance. Okay. Now on the right, you can do the same thing, but you can use a right tail. So let's see if they have a right. Okay, so let's put the conditions first. Decision, conclusion, conclusion. So here I'm going to base it on a rejection region. If my sample statistic for the left tail test, if my sample statistic is less than my critical value, then I'm going to reject. Otherwise, I'm going to fail to reject. Okay? So here we fail to reject. On the right is going to be an F dot inverse, but I'm going to use a right tail distribution because now on the right side, what is the F value such that the area to the right is equal to alpha, right? So you do that and you put in the same thing that we did in the previous one. So we have degrees of freedom in the numerator and then degrees of freedom in the denominator. Okay? And then again, you can copy and paste this thing here. But in this case, if B6, if your sample statistic is greater than this statistic over here. Okay? And then that would be a right tail test. And if you want to do the two tail test, you have to do you have to find the F value because it's not symmetric distribution. You have to find the F value on the left tail where the area to the left is alpha over 2. And on the right tail where the area is alpha over 2. So you need two values over here. And for the two tail, so I'm going to copy these actually. and I'm going to put here, so what was my alpha was B5, right? I'm going to put B5 over 2, so that gives me, and this one should be B2, and this one should be B4. And same here, this would be a B5 and B2 and B4. Okay, so for a two-tailed test now, alpha over 2. Okay. For a two-tailed test, if we were doing a two-tailed test, then our rejection region is in the two tails. So we have to check if our sample statistic is either in the left rejection region or in the right rejection region. Okay? So this would be an OR statement here for two tails. There's an example with two tails at the end of this. And so we would do here if, and I need to do an OR statement, or my sample statistic, if it's less than the left value, or if my sample statistic is greater than the right tail value, then I'm going to reject. Otherwise, I'm going to fail to reject. Okay? In this case, this doesn't apply, but if the student was saying that the variances are different, if his claim is that the variances are different. Okay, so we fail to reject the null hypothesis in this case. Yeah.
When does the, maybe this doesn't even relate to this problem, but when does the p-value come into play?
The p-value is just another way to make it always comes into play. Okay. And all we've done, the p-value is just another way to determine the conclusion of your hypothesis test. So rather than finding a rejection region, your p-value calculates the area to the left or right of your sample statistic and compares that to alpha directly. Because when you're looking at, so let's look at this here. Again, one last explanation for p-value. Okay, so the p-value, in the rejection region, you visually say if this is smaller than this critical value, then you reject. If it's great, let's say in a left tail, if it's greater, you fail to reject. The p-value, what it does, you already have the area in pink. That's alpha that's given. You calculate the area to the left of your sample statistic. If the area is greater, then your sample statistic is larger than your critical value, obviously, and therefore you fail to reject. If it is less, if the area to the left of your sample statistic, so if your sample statistic was here, the area to the left would be less than alpha. That's then the area to the left of the critical value, and then you would reject it, okay? So the p-value, there's just two ways of making the same thing. I like the visual rejection region because it just kind of makes sense to me, but so you can do either.